So welcome everybody to our fourth seminar of the Algebra, Particles, and Quantum Theory seminar series. So I'm pleased to introduce to you tonight's speaker, Howard Barnum. Howard was recently a visiting professor at the University of Copenhagen and was also a Riemann Senior Fellow at Riemann Institute / Institute for Theoretical Physics at Leibniz University in Hanover. Howard did his PhD at the University of New Mexico under the supervision of Carlton Caves. Later, he took a postdoc position in Massachusetts and then a research position at the University of Bristol. From here, he returned to New Mexico to work in a large variety of roles, including as a staff scientist at the Los Alamos National Laboratory. He spent a year as a visiting researcher at Perimeter Institute. Howard is known amongst his colleagues as a free spirit, which is easily demonstrated not only by his eclectic academic interests, but also by his eclectic interests in the real world. He maintains a blog on art, music, culture, science, public affairs, philosophy, and life called Wine, Physics, and Song. Howard started his studies in philosophy, then moved into economics and finally physics, where he has worked in quantum information and quantum computation when they were newly emerging fields. He has also worked extensively in quantum foundations. And today, Howard will tell us about some of this work in quantum foundations, relating in particular to Euclidean Jordan Algebras. Now, before I begin, I'd like to emphasize that everybody who showed up today is here to learn. So I would hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, of course, that's not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Howard, anytime you're ready, please go ahead.
All right. Well, thanks for that introduction and thanks for inviting me, Cohl.
Yeah, my pleasure.
I wanted to check on the raising hand. Is there a little yellow hand that goes up that I can see? Or how does that work?
If so I can see, yeah, Hillary just did it. So no, that was an excellent example.
Okay, good. So it will pop up on my screen even if I don't have all the participants visible.
Yes.
And then do I need to do anything to respond or?
So I can, usually I've been taking care of that. So okay. I've just been watching and then I will unmute people and I'll try to generally find a good time to interrupt you.
Yeah, sounds good. Because I do want to make sure that, people follow along. Since it's a mathematical physics oriented seminar, I thought I would go into a little more detail on the mathematical background of things than in my most recent talk, which was in a Vienna Quantum Foundations conference a couple months ago. And I think most of the detail is going to be about the basic properties and important results on Euclidean Jordan algebras, rather than necessarily the proofs of my results, which, while they're beautiful, of course, might be a little bit less useful for people to see the details of. So I wanted to make it useful for people in various areas of physics to see what they might be able to use Jordan algebras for. Or just to appreciate the beauty of some of these results. I should mention that Joachim Hilbert, who's a professor of mathematics at the University of Paderborn in Germany, was my co-author on one of the new results I'll present, and Cosmin Ududek, who is now involved in this cool startup that, well, okay, it's been around for more than a decade, so, but very successful company. He's currently based in London, and if anybody's into machine learning applied to problems of big data and so forth, it's probably a great place to work. He's a really nice guy. And he's still interested in keeping up in this foundation stuff. But a lot of this originated at Perimeter, around 10 years ago or a little more, the work with him. Okay, so the basic plan of the talk, I'm going to introduce Euclidean Jordan algebras. They're abstractions and generalizations of the mixed state formulation of quantum theory over the complex numbers. And then I'm going to introduce the so-called general probabilistic theories framework. And I'm going to view Euclidean Jordan algebras from that perspective as potential systems in a probabilistic theory, of which quantum mechanics, for example, and classical probability are just particular examples. And then I'll present two new axiomatic, if you like, characterizations of the class of Euclidean Jordan algebraic systems from this general probabilistic point of view. So that's the overall plan. So to introduce Jordan algebras, they were actually introduced by Pascual Jordan early in the history of quantum theory, and precisely as a slightly more general, perhaps, algebraic setting for quantum theories. And he basically abstracted properties from the symmetric product of Hermitian matrices, because the symmetrized product returns a Hermitian matrix, whereas the ordinary matrix product does not preserve hermiticity. So he thought maybe, we want to preserve the observables in order to understand the algebraic nature of things. So it's just a real vector space with a commutative bilinear product, so an algebra over R, that satisfies a special case of associativity, but is not associative in general. And the special case is this Jordan property. So if we have three A's and a B, you can have A squared, which is just the Jordan square, with A dot B, or you can move one of the A's into the last parenthesis.
Could you make a comment on the purpose of this second axiom?
That's a good question, very good question. And I have to just say, it works. I mean, it is satisfied by the, let's just say a general commutative algebra is a very general thing. Commutative non-associative algebra, there's tons of them. So you need more specific properties to capture the something close to the Hermitian matrices. And so you can just directly verify that it is satisfied by this product. I don't actually know how Jordan came up with it. And if anybody, does anybody know of a intuitive justification for it?
I think I remember hearing, I might be misremembering, which is why I asked, but this property might be sufficient to be able to write exponentiation of objects in the algebra. I'm not sure if that's the answer or not, but that is what I vaguely remember.
I mean, it certainly is sufficient because there is a spectral theorem for Jordan algebras, and you can use that to define exponentiating them. So yeah, maybe there's even a more algebraic way of seeing that without going through the spectral theory. So yeah, I would not be surprised if there is some direct way of using it in the exponential. So yeah, interesting observation. So let me actually just write down. Yeah, so I might as well take the opportunity to learn some things too. So yeah, look into whether the link between exponentiation and the Jordan property. Okay, I just want to say one more thing. We call it Euclidean, or an Euclidean Jordan algebra, if you can introduce an inner product such that A dot B inner product with C is equal to A inner product with B dot C. And people often call this associative, but the real, that's kind of, it looks sort of like moving the parentheses. The real significance of it is that the Jordan multiplication operator, which takes anything X in the algebra to B times X, is self-adjoint with respect to this inner product. And since it's a real, self-adjoint just means symmetric. And of course, later mathematicians did go on to study Jordan algebras over arbitrary fields, certainly infinite dimensional cases, even over R, ones that aren't Euclidean. They have a lot of interest in application. We're going to be interested in the ones over R. I'm going to confine it to finite dimension, although many of the results will generalize to infinite dimension. And I'm just going to note that originally, the concept that Jordan and actually von Neumann and Wigner used was not directly Euclidean, but formal reality. So it says that if the sum of two squares is 0, each of the things that got squared must have been 0 to start with. And we'll see why that's relevant. So we can define the state space of a Jordan algebra. And normally, so if it's Euclidean, it has a unit in particular. And we just define the trace as the inner product with the unit. One once you have the spectral theory, you can also define the trace as the sum of the spectrum. But do this for now. So the trace inner product is an example, which xy is the trace of the product of x and y, is an example of a associative inner product for Euclidean algebra. And inner product is unique up to positive scalars on a simple Euclidean Jordan algebra. We'll say what simple is in a second. Otherwise, you can dilate it by different positive factors on the different summands, and still have it be an associative product for that Jordan algebra. Okay, the normalized state space then is going to be the compact convex set, which I usually call omega. It's just the set of everything in the Jordan algebra whose trace is 1. And let me take that back. Yes, that should actually be everything in the positive cone of the Jordan algebra. So the positive cone of a Jordan algebra is the set of squares. Later, when we define the spectrum, you can equivalently define it as things whose spectrum is non-negative. So yeah, sorry, this should be the set of omega in V plus the positive cone whose trace is 1. So, you know, the positive cone, it's the positive semi-definite matrices in quantum theory, standard quantum theory, and we're looking at the density matrices. Generalizes nicely to Jordan algebras. Okay, so we can use the inner product to identify the Jordan algebra with its dual, and we often do. And then you can think of states as maps that take an observable to the inner product of the state and the observable, which we think of as the expectation value of the observable in the state. And this was, you know, all of this was kind of in Jordan's motivation for introducing it. Pure states are extremal points of this normalized state space. They can't be written as non-trivial convex combinations of other states. Those are just the rank 1 projectors in quantum theory, projectors onto some Hilbert space state. Okay, and I said the Jordan squares are a topologically closed convex cone. They span the Jordan algebra as a linear space. And here's where formal reality is useful. It says the cone is pointed, so it doesn't contain any complete line. You see, if we had a squared plus b squared that were equal to 0, you'd have a complete line. It would be the line through a and b, or rather a squared and b squared. It would be the line through a squared and b squared. That would be in the cone. And so the cone would have a non-trivial edge. It'd really be a wedge. And then when we slice it with this normalization plane that says trace is 1, we wouldn't get a compact set. So the formal reality gives you a compact convex state space. And it's equivalent to Euclideanity in finite dimension. Now what happened here? Yeah. Okay, I mentioned simple algebras. So most people probably know what an ideal in an algebra is. It's just a subspace, and it turns out to be a subalgebra I, such that it's kind of absorptive. If you take anything in the algebra and you hit it with I on the left or on the right, I hit it with something in the ideal on the left or the right, the result is in the ideal. So an algebra is simple if it has no non-trivial ideals. And then every Euclidean Jordan algebra is a finite product of simple factors. If you think of it as a vector space, that means it's just a finite direct sum of these simple summands or simple ideals. Yeah, and I guess they're called factors because it has this product form. So, you know, and the Jordan product is just on a non-simple algebra, you know, it just breaks down into doing the Jordan product in each summand, not surprisingly. You can think of them as simple ideals as super selection sectors because all of the pure states are going to lie in one or the other of its simple ideals. So there's no coherence between them, essentially. So basically, if you want to understand Jordan algebras, you can concentrate on the simple ones. And if you're dealing with a non-simple one, almost everything else is sort of trivial to extend to it. So Jordan, von Neumann, and Wigner in the 30s classified the simple finite dimensional formally real Jordan algebras And just a second, I'm going to close the door here so I don't. Did I close the door, Rana? Yeah, they classified them up to isomorphism, and basically they are three classes. There's the matrix ones, we can think of them. They're self-adjoint matrices over the reals, the complex numbers, or the quaternions. And the Jordan product is just the symmetrized matrix product. The positive cone is just the positive semi-definite matrices, and so forth. We can think of this as real quantum theory, complex quantum theory, and quaternionic quantum theory. Then we have the spin factors. I mentioned these before. This is just p, if you want to think of them as p space dimensions and one time dimension, you can introduce a Jordan product, which is this, basically. Just involves a dot product on the space-like part. Well, there you go. This is just the dot product, and right. And what is the normalized state space here? It's just a ball. Yes, a p-dimensional ball. And then there's the exceptional Jordan algebra, which we can think of as 3 by 3, I should have said Hermitian octonionic matrices, right? I mean, you have a conjugation on the Hermitians and the quaternions with which you define Hermitian using the conjugate transpose as usual. And again, symmetrized product. Everything works like you might expect. So it's very close to quantum theory. And what we find is when we're doing axiomatic characterizations, attempting to characterize quantum theory, we often end up with the Jordan algebras. Okay, general probabilistic theories. I'm going to go rather fast over this. It's become a very active field of research nowadays, inspired by quantum information, because it's a good framework for thinking abstractly about what is the nature of information as embodied in physical systems, on which you can do various manipulations, prepare various states, do various measurements, and what you care about is the probability of the measurement outcome conditional on the state and maybe on some other manipulations you did in between preparation and measurement. So it kind of has origins even in quantum logic, starting as early as the 30s, because people talked about states on quantum logics, and they're a bit more general than quantum theory. And through the 60s, these are some of the references. John Barrett actually coined the term general probabilistic theories in 2005, and Lucian Hardy wrote a very important paper that really brought these ideas to the attention of the quantum information community, and also had a derivation of quantum state space in the formalism. So a major concern, although not the only one in this program, is to formulate principles, whether they're just mathematically appealing or hopefully of physical significance or in terms of information processing meaningful, that characterize, or some like to say reconstruct, a quantum theory in the framework. You know, people often say, well, we need a principle-based characterization of quantum theory, not one that's just based on the mathematics of Hilbert spaces and Hermitian matrices. Sometimes they say it should be more like the formulation of general relativity in terms of the equivalence principle and the maximum speed that anything can go, and so forth. Okay, and I should emphasize that when we characterize quantum theory in this framework, in a sense, we're characterizing extreme idealization because it's an arena for physics. We often think about all density matrices as preparable, all POVMs as measurable, all potential dynamical evolutions we consider, you know, maybe if we're thinking about what an opponent Eve could do, we say we want something secure against anything she could do. So it's kind of the information theoretic picture. And then, of course, some of these things are very hard to do, as we know from trying to construct quantum computers. But it's sort of this idealization of the state space that is often the target for study in general probabilistic theories. Although you can formulate circuits and so forth in the framework and talk about computation, and people have done that. Okay. All right, so a little more detail. I'm going to go very fast over this. Yeah, we've got a compact convex set of states. I said what pure states are. They're extremal in the convex set. Affine maps, that means they preserve linear combinations where the coefficients sum to 1, are candidate dynamical evolutions. And it's basically because they commute with convex combination. That's desirable in an information theoretically sensible theory. We often study the automorphism group of the state space. So these are symmetries, or if you like, candidates for reversible dynamics. They're the group of affine maps from the space to itself that preserves the normalized state space. It takes it onto itself. So you can't like decohere it, squish it in any way. It has to be preserved. Okay. And if you want, you can make the space into a, well, right. So it turns out the automorphism group of the state space fixes the center of gravity. And then you can even introduce a Euclidean inner product such that these automorphisms are a subgroup of the orthogonal group. And this is all happening on some affine space, which think of it as, in the quantum case, it's the trace 1 Hermitian matrices. But we usually like to linearize. Oh, okay. Well, here are some examples. Let me go. All right, well, let's stay with the affine space for the moment. Let me just give some examples of state spaces. This is a real bit. It's a disk. A classical bit is just a straight line. A classical 3-state system is a triangle, and these red things are the extremal points. Red dots are the extremal points, the pure states. Square is often an interesting state space, provides counterexamples to many things. It's involved in the Popescu-Roerlich PR box, stronger than quantum correlated entangled states, for example. Okay. What about effects and measurements? Well, everything's affine because we want it to commute with convex combination. So effects are affine functionals from this ambient space to the reals, such that they are probability valued when evaluated on normalized states. So that's natural to associate with a measurement outcome, because it gives the probability of the measurement outcome when you put in a state. We have the unit effect. This should say U of omega is 1. So it's equal to 1 on, okay, yeah, it's actually equal to 1 on this whole affine space. But in particular, it's equal to 1 on the normalized state space. And then measurements are, let's just take discrete, or even, yeah, discrete measurements. They're index sets of effects that sum to the unit effect. And that just ensures that the probabilities add to 1 no matter what state you put in. Okay, and we can give them the pointwise ordering. One effect is bigger than the other if it's got higher probability in every state. And then the set of all effects in this ordering is just the interval between 0 and U in the affine functionals on the state space. So 0 being the 0 functional. And so these affine functionals are actually naturally a vector space where the effects live. If you want, you could specify an allowed or physical set of effects that's smaller than this full set of mathematically consistent effects that return probabilities. Usually take it to be convex to contain the unit effect, and to be closed under effect goes to unit minus the effect. And the reason is basically that if you could measure something, you want to also be able to measure its complement, so you have complete measurement. So we say the no restriction property effect version holds if the set of allowed effects is the whole interval of effects. And that's very frequently assumed in this framework. Okay, and the quantum case is familiar. The effects are the trace with a POVM element, which is just a positive semi-definite matrix between 0 and the identity matrix. Okay, so we have a vector space where the effects live. We usually linearize the state space too. So we embed this normalized state space in a vector space 1 dimension higher, as the base of a regular cone of unnormalized states. And so we just take all the rays from 0 through a normalized state, and that gives us a cone. And those are the unnormalized states. That's the positive semi-definite matrices. So this is how we usually do quantum mechanics. We take all the Hermitian matrices, not just the ones that have trace 1. Okay, and this is what a cone is: subset closed under non-negative linear combinations. It's pointed. We talked about that before. If it contains no complete line, and I guess we call it regular if it's pointed, generating, and topologically closed. By the way, can you see the little hand on my screen when I'm pointing to things?
Yes.
Okay, good. All right, and then we have this automorphism group of the normalized states, and it just extends to a representation as a subgroup of the orthogonal group on this whole space, if we choose, extend the inner product in the obvious way. And now it fixes all multiples of the centroid of this state space. And now this is an ordered linear space. In fact, it's the dual of the space where the effects live, although I usually think of it as the other way around, the effect space as the dual space. Meaning, one thing is bigger than the other if there are differences in the positive cone. Okay, so as I mentioned, the set of effects generates the dual cone. If we take all non-negative multiples of effects, in fact, we get the dual cone. And the dual cone is just the linear functions that are non-negative on V plus, which is the unnormalized state space. So it's just a generalization of quantum, the description of a finite dimensional quantum system, but we can use an arbitrary convex compact set as the state space instead of the space of density matrices. Why did we bother to linearize? Well, one good reason is to represent dynamics conditional on observations. So let's define a positive map as just a linear map that takes the positive cone into itself. And now if we look at its dual map, which acts on the effect space, and it's defined, just the way you define adjoint normally, using the pairing. If it takes effects to effects, then it's a reasonable candidate for probabilistic dynamics, right? If it takes effects outside of the effect, the set of effects, then it's violating your assumptions about what measurement outcomes are. And so we can take this unit effect evaluated on tau of omega as the probability of process tau, where tau is one of these positive maps that satisfies this condition for not increasing probabilities above 1. And another useful concept is the order automorphism, and that's a positive map that actually takes the cone onto itself. And these form a Lie group, which I call aut V plus. It contains, but is larger than the symmetries of the normalized state space, because it doesn't have to preserve normalization. And there's a physical interpretation of the ones that reduce normalization, namely, you can take the trace and see what the probability of that happening is. And in fact, if you take a list of positive maps, tau sub I, we usually call it an instrument. If they sum to a trace preserving map, equivalently if they're duals sum to a unit preserving map, that's a complete instrument. And we can think of that maybe as an experiment where we have outcomes I, but something comes out and we are keeping track of also of what the post-experiment state is. Or it could be another physical process. We don't have to do an experiment. Maybe nature does and gives us some information. Okay. Reducible cones connect to simple Jordan algebras, but they apply generally to these general probabilistic systems. So we say a cone in a vector space is reducible if the vector space is a direct sum of the two spaces. So they don't two subspaces that don't intersect but span the space. And every extremal ray of the cone, so that's just the extremal rays of the cone are just the multiples of pure states, is either in V1 or in V2. And so we say that a cone is irreducible. I should have said V plus is irreducible if it has no such decomposition into summands. So the interpretation is there's no coherence between these two summands if the cone is reducible into those two summands. Every finite dimensional cone has a unique decomposition into simple, simple, I meant irreducible here, into irreducible summands. And for Euclidean Jordan algebra state spaces, if the algebra is simple, the cone is irreducible. And let's take the example of the n-state classical system. Sorry. It's just a direct sum of one-dimensional state spaces, the real numbers with positive cone, the positive reals. And then the normalized state space is just a simplex. So that's like the extreme example of a reducible cone. All right. Any questions up to this point? Okay, I will try to go pretty fast. So, oops. Now it's often convenient, and many people actually start this way, to represent the dual cone in the same space as the states. So the effects and the states in the same space. And you just do it by picking an inner product on the state space. And then we say the internal dual of the positive cone relative to this inner product is just the set of things that have non-negative inner product with stuff in the primal cone, let's say the state cone. It's isomorphic to the dual cone described as a cone in the dual space because we just identify an element of the primal space with the functional take the inner product with me. Okay, and then if you can find an inner product, and I should emphasize that by inner product, I mean a positive definite one. So X, inner product X has to be non-negative, relative to which the internal dual cone is identical with the primal cone, then we call it self-dual. And some of my collaborators like to call the inner product self-dualizing, which is convenient to have a word for it. So the positive cones of Euclidean Jordan algebras are self-dual. If you think about quantum theory, we use the positive semi-definite matrices for both states and effects. And that generalizes to Jordan algebras. And the associative inner products are indeed self-dualizing because we just use the trace inner product, for example. Minor point, self-duality is stronger than the cone being affinely isomorphic to its dual, which we often call weak self-duality. The cone with a square base is an example of that. It is weakly self-dual, but not strongly self-dual. Okay, embeddings of, let's see, GPT systems. I'm going to have to go. Well, let's just say this quickly. So we can think about embedding one GPT system into another. So here we have a vector space that contains the states and the set of effects, and we have B's state space and its effects. So an embedding is just a pair of linear maps of the ambient space for the states and the ambient space for the effects, which is the dual space, such that for any state and effect in the first, when we apply the map and evaluate probabilities after applying the map, we get the same probabilities we had before the map. So that seems reasonable. We can reproduce the probabilities. And it's a linear map, so it preserves the convex structure, which we definitely want. Okay. And then we say systems are isomorphic if each embeds into the other. And I won't go too much into this detail. Basically, it allows you to, having these two maps allows you to define a positive projections on the second system's effect space and state space, such that its image is the embedded first system. Okay, I'm going to skip that detail. Yeah, I'd like to, well, okay, let me just say a little bit about the automorphism groups of these things. So the automorphism group of the positive cone of a Euclidean Jordan algebra is the reals times a semi-simple group. And the reals are just dilation of the entire cone by a constant factor. And then what's G? Well, to take an example, in ordinary quantum theory, G takes a Hermitian matrix X to the Hermitian matrix AX A dagger, where A is a non-singular complex matrix, any non-singular complex matrix. So element of GL of the underlying Hilbert space. So it's a one element CP, like a CP map with one Krauss operator, and the Krauss operator is non-singular. Okay, that actually extends. So I have some information about this is the Lie algebra of the automorphism group. So for the real symmetric matrices, it's just SLM of R Hermitian, SLM of C, that's this matrix A that you do AX A dagger by, and it's SLM of H. So in each case, you're just going X goes to AX A dagger. You take either real matrices, complex matrices, or Hermitian matrices. And you can kind of define that for octonionic matrices too, if they're 3 by 3. Octonions are not associative. That's why you can't do this kind of thing for arbitrary dimension. But you can kind of get a way of making that to work for the octonion. So that's how they slip in. And here, this is just, the Lie algebra of the Lorentz group. Okay, and I should emphasize this is for the semi-simple part. Oh no, okay, here I added the R, so that's fine. Okay, I won't go into all the detail, the other detail here yet. Well, yeah, maybe I should. So every semi-simple group has has many maximal compact subgroups, and you can pick them out by looking at the one eigenspace of a Cartan decomposition. There's or Cartan involution, so-called. And there are many Cartan involutions, and they pick out different maximal compact subgroups. So there's one for which the automorphism group of the normalized state space, in this Jordan case, is the stabilizer of the unit, the Jordan unit, in the automorphism group of the whole positive cone. And we have the ambient inner product, which is the Jordan algebra inner product. And indeed, if we take the part that intersects the part of the automorphism group that is orthogonal with respect to that inner product, the subgroup of the orthogonal group, that's the symmetry group of the normalized state space. It's also the automorphisms of the Jordan algebra. And you can pick it out with the Cartan decomposition. G equals K plus P. K is its Lie algebra. It consists of skew adjoint, so anti-symmetric matrices. And the P part is the self-adjoint. And in fact, P can be identified with the Jordan algebra itself. And I guess I'll come back to that if we need it. The positive cones of EJAs are precisely those regular cones whose interiors are Riemannian symmetric spaces. And the symmetric spaces means not only are they Riemannian spaces, the automorphism group acts by isometries, so it's a symmetric G space. And the symmetry means we can find a global isometry that at any point we can find a global isometry that fixes that point and reverses the geodesics through that point. I won't say too much about it. You get it by dividing, you can think about it as dividing the semi-simple group by its maximal compact subgroup. That gives you, for instance, in the Lorentz case, this would give you a symmetric space that is a hyperboloid inside your Lorentz cone and a constant determinant. And then the reals give you the whole cone by just taking rays through that hyperboloid. So this is an irreducible symmetric space. Okay, that was useful in the proof of one of our results. I don't think we're going to actually use it, but it's an important mathematical fact. Spectral theory. An idempotent is an element in an algebra that squares to itself. And a primitive idempotent is one that can't be written as a non-trivial sum of idempotents. And so for simple Euclidean Jordan algebras, we have a spectral theorem. Every element is a real linear combination of primitive idempotents. And if it's in the normalized state space, it's a convex combination of primitive idempotents. And in fact, The primitive idempotents are the pure states. Think rank 1 Hilbert space projectors in the quantum case. Okay, we define a Jordan frame. It's an ordered set of mutually orthogonal idempotents. So their Jordan products are delta ij times ei itself, or equivalently, they're orthogonal with respect to the Jordan inner product. The automorphism group acts transitively on the set of Jordan frames. This is a great reference for a lot of stuff I've been talking about. And you can find the proof in there. So this transitive action is a generalization of the fact that in quantum theory, any orthonormal basis can be taken to any other by conjugation, by a unitary. Okay. Is there a way of characterizing ordinary quantum theory of the complex numbers within Jordan algebraic theories? Well, yes, there are several ways. And one of my favorites is to add something that in a paper with Kosmin, Ududek, and Markus Müller, we called energy observability. It's closely related to notions of Cones and Alfvén and Schultz, orientation and dynamic correspondence. What we say is that the automorphism group of the normalized state space, the symmetry group, is non-trivial. So it has a non-trivial Lie algebra. And then we want a linear injection of that Lie algebra into the observables. And you can think of that as Hamiltonians being injected into observables. And in fact, in quantum theory, that injection is actually a bijection in complex quantum theory. Except that we want, it's a bijection to the traceless observables in quantum theory. We want it, right, we want the image to be proportional to the order unit, which is after all fixed by the symmetry group, if and only if the Lie algebra element is 0. And we also want that the image, so the observable, that is the image of a generator of dynamics, is fixed by the dynamics generated by that observable. So that's kind of a Noether's theorem-like property. John Baez has a nice paper on this stuff that came out recently, reviewing a lot of stuff that's related to this. So what does this injection turn out to be? Well, this gives you complex quantum theory. And the objection is just that observable goes to I times the observable as the generator of dynamics. Oh, sorry, that's actually backwards. It's a bijection in the quantum case, and I gave the inverse. Okay, and Cones orientation is a complex structure on the automorphism group of the cone that's compatible with the Jordan structure. So it's not surprising that it's also related to this. We defined, our definition didn't refer to the Jordan structure. It's completely convex, but I think it makes the most sense when you have a spectral property for the observable space. Anyway, that's, I think, a very important way of characterizing quantum theory within the more general setting of Jordan algebras. Okay, other things that characterize it, well, if you require that a composite, every system has a composite with itself, there's also Jordan algebraic. That's only true for complex quantum theory. It's paper, you can kind of get that out of this paper by Massanis and Müller by thinking about Jordan algebras and extending it to the non-simple case. And if you're interested in symmetric informationally complete POVMs, which it's hypothesized exist in all dimensions in complex quantum theory, they don't exist in all dimensions for the correct generalization of them. Does not exist, for example, in real or quaternionic quantum theory. So that might also be another way of picking out a complex. Okay. I talked about embedding. It turns out the, well, they're except for the exceptional one, all of these Jordan algebras have embeddings in complex quantum theory. I should point out they're kind of ones, relatively simple ones. For the quaternions, you blow them up. You can blow them up, each quaternion into a 2x2 matrix, and you just get a bigger complex matrix. And the self-adjoint ones are complex self-adjoint, and it works nicely. The spin factors are kind of cool because they go into Clifford algebras. So if you have, let's say, a 2K dimensional ball, you get like K qubits, and then a subspace in there generated by various strings of Pauli matrices is your Jordan algebra. So I think there's a lot of physics in there. I'm not going to have time to talk about it, unfortunately. These are actually the only GPTs that are non-restricted. So the effects generate the full dual cone that embed into quantum theory. Very interesting. Andy Garner and Marcus Mueller recently observed this. It's also in Reinhard Werner's PhD thesis. Okay, we'd better get now to the two characterizations I want to present that are the new results. And as I mentioned, I'm going to describe them. I think it's much more interesting to describe them and think about the properties rather than give the proof. So we'll say a sequence of states is perfectly distinguishable if you can find effects E1 through En that are a complete measurement, or at least a subset of a complete measurement. So you can measure them simultaneously, such that EI evaluated on omega j is delta ij. So that's just saying, if I get result I know, given that I know one of these states prepared, I know it was state I, not any of the others. If the omega I are pure states, we're going to call it a frame or an n frame, if you want to emphasize how many. And it's maximal if it's not a proper subsequence of any other frame. I don't think we really use that, but okay. Order matters. Different orders, different frames. And I'll tell you why in a second. Fewer effects. So if we did have a restricted system, well, we might have less distinguishability if we cut down the effects. So the set of frames depends both on the states and effects. But when it's unrestricted, it depends only on the state space. And although we defined, well, okay. Yeah, here we just defined distinguishability and frames using the full set. So we're going to define later spectrality and strong symmetry. They're properties of the convex set because we define them relative to this. So the full set of effects is determined by the convex set. Okay. All right, I will give the result and then define the two properties on the next slides that we use in the result. Any finite dimensional complex convex set that is first spectral and second strongly symmetric is the space of normalized states. Is my control bar getting in the way here, or am I the only one who can see it? I guess I'm the only one. Any finite dimensional complex set that is spectral and strongly symmetric is the space of normalized states of a simple Euclidean Jordan algebra or a simplex. So a simplex is not simple, although it's the state space of a Euclidean Jordan algebra. And here are the two references. This is the published paper. If you want something close to the published version, go to my blog. The archive version they're both nice in their own way, but there's a lot of overlap. This journal, I'm curious if anyone can access it. It's a big venue for lead theorists, but I think it's sort of run by the community, and I'm not sure how well available it is. Okay, so here's spectrality. For every state, there is a frame such that the state is in its convex whole. In other words, it's a convex combination of perfectly distinguishable pure states. And strong symmetry says for every size of frame, the automorphism, the symmetry group, the state space, acts transitively on the set of frames of that size, which means it can take any such frame to any other such frame. And because order matters, that means it can also arbitrarily permute the elements of any given frame, as we can do in quantum theory. So we're just abstracting the spectral theorem for quantum states, or indeed Jordan algebras. And the fact that for any two orthonormal sets of rank 1 projectors, you can find a unitary that takes one to the other by conjugation, including just permuting. So I didn't specify that these coefficients are unique, but in fact, with both assumptions, they are unique up to a permutation. And we can also get no restriction for free, even if we did define distinguishability in terms of a restricted set of effects. If you have these two properties, you can't have the restricted set of effects. Okay. So that's the result. A little bit of motivation. You can gloss it as saying every state belongs to some classical subsystem, because the convex hull of a set of perfectly distinguishable pure states is like a classical system. And that actually does relate things to quantum logic, because orthomodular lattices are kind of a logical way of pasting together a bunch of classical logics into a non-classical logic, but it describes the lattice of state spaces of quantum systems. And also, properties like this are often used along with energy observability sometimes in quantum thermodynamic protocols. And you can generalize a lot of these protocols to the Jordan algebraic setting, as long as you don't need to measure the energy. If you do, then you're looking at quantum theory. Okay. Yeah, in the interest of time, maybe I should mention this builds on an earlier paper where we had one extra axiom, no higher order interference. So Joachim and I basically got rid of that axiom. We got characterized the same set of systems. And we used some intermediate results from there. For a while, I kind of hoped there were a lot of theories that had higher order interference plus these two nice properties, spectrality and strong symmetry, but no dice. And various people have looked in the GPT setting at nice properties or bounds that you can get using strong symmetry and spectrality. And now we see that those really only apply in the Jordan algebraic setting. So they're not as general as one might have hoped. Okay. To get to the second result, the second characterization, I'm going to introduce the fact that the cone of unnormalized states is homogeneous. And also that we have continuously reversible pure state transitivity, which is a mouthful. So homogeneity just means, and it's defined down at the bottom here, I think we talked about the automorphism group of the cone already. A cone is homogeneous if it's interior, if the automorphism group of the cone acts transitively on the interior of the cone. So any interior point can be taken to any other interior point by an automorphism of the cone. Okay. And continuously reversible pure state transitivity just means that any pure state can be taken to any other pure state by an automorphism of the normalized state space. Lucian, for instance, used that in his 2001 characterization, or maybe it was 2000, I believe, of quantum theory. Okay, so the result, our result is going to be if you have homogeneity and continuously reversible pure state transitivity, you get the same set of state spaces as in the other characterization, except you don't get the classical ones. You just get the simple Euclidean Jordan algebras. Okay, before I talk about that, maybe I'll quickly mention the Kosher-Winberg characterization of Euclidean Jordan algebra state spaces. It says that any irreducible finite dimensional self-dual cone, if it's homogeneous, then it's equivalent, affinely isomorphic to the positive cone of Euclidean Jordan algebra. No restriction to simplicity in this theorem. But that's a major, major result on Euclidean Jordan algebras and their positive cones. self-dual homogeneous cones are the positive cones of Jordan algebras. I will skip this proof sketch. This is an example of a non-self-dual homogeneous cone. It's the lowest dimensional one, in fact, and it was introduced by Winberg. You can think of it basically as two positive semi-definite matrices. There's this lower square, and there's the corner elements, and they're stapled together because they overlap in one element. So in fact, you can even think of it as a pair of two positive semi-definite matrices. And actually, right. So you can show that it's homogeneous, but not self-dual. And interestingly, Hideyuki Ishii gave examples, even continuously infinite families of non-self-dual, but weakly self-dual such cones. This is not one of those examples. And in higher dimension, in fact, you get continuous families of these homogeneous cones. So our new characterization, and this is from joint work with Kosman, that's not out yet, a general probabilistic theory that is homogeneous, so it has a homogeneous cone of unnormalized states, and has continuously reversible transitivity on pure states, is irreducible and Jordan algebraic. So it's a cone of a simple Jordan algebra. We don't have, the classical systems aren't in here because, of course, their automorphism group of the connected automorphism group of their normalized state space is trivial, so they don't have continuously reversible transitivity. And I should have stressed that continuously reversible transitivity means that the connected identity component of the symmetry group of the state space acts transitively on the pure states, because obviously the full automorphism group of a simplex does act transitively on its pure states. It's just a permutation group. Okay. So I mentioned this continuously reversible pure state transitivity has appeared in many characterizations of quantum state space, not only Lucian's, but there's a nice one by Muller and Massanes that uses this plus the existence of entanglement. There might be a thermodynamic motivation for it. I think von Neumann used it in arguing that the quantum von Neumann entropy was the correct thermodynamic entropy for quantum theory. And even the non-continuous version of it enables you to do things like teleport in suitable composites and so forth. So I think I'd like to end by just saying a few words about motivating. So that's a little bit of motivation of continuously reversible pure state transitivity. The motivation of homogeneity, I think, is kind of interesting. So I first encountered the Kosher-Winberg theorem, in fact, in Haag's book, Local Quantum Physics. The second edition has an extra, I think only the second edition has this chapter, where he cited this Kosher-Winberg theorem and argued that homogeneity was well motivated as being able to prepare any interior state from any other. But you can do that in any GPT just by throwing away whatever state you have and preparing the state. I mean, that's a positive map. So the special thing here is that you can get from any state to any other state by an automorphism of the cone. So what's special about that? Right, so just like throwing away the old state and repreparing it, that destroys entanglement with any other system, destroys coherence. But automorphisms are sort of intuitively maximally entanglement preserving, coherence preserving. And they figure in a lot of quantum information protocols like teleportation, steering, ensemble steering. It takes advantage of the fact, if you look at the mathematics of it, that there are a rich automorphism group, and in fact, it uses the homogeneity. So it's a very unusual property for GPTs to have this homogeneity, and it's important in coherent information processing. There's also an interesting sort of Bayesian, or maybe you might want to call it Cubist, in the sense of Chris Fuchs and collaborators' point of view. Matt Leifer also likes this. We've discussed it. You can think of, remember, operations condition the probabilistic description of state on an observation. These possibly normalization decreasing positive maps. Interior states are particularly interesting because they rule out no measurement outcome. So now you might argue that, well, you should never completely rule out a measurement outcome. The boundary of this finite dimensional cone, which does contain states for which some measurements have probability 0, that's just a useful idealization. And if you want to, you can approximate boundary states arbitrarily well by interior states. So the order automorphisms are non-drastic operations. If you didn't have any measurement outcome ruled out before, you stay in the interior and you haven't ruled out any measurement outcome afterward. So maybe we might want to think of that as, the way conditioning really should work. Okay, somehow there we go. Another way of thinking about homogeneity, but related, is that it's equivalent to the affine isomorphism of all bases for the cone, right? And basically the reason for that is that the dual of a homogeneous cone is also homogeneous. So I can take the order unit to any, if I take the order unit's an interior point, the normalization functional, I can take it to any other interior point, use that as a normalization functional, and that cuts out another base for the cone. And you can cut out all possible bases for the cone that way, all ways of using that cone as the unnormalized state space for some system. Those are not affinely equivalent in general, but they are affinely equivalent for a homogeneous cone. So that's basically saying, if we do this kind of non-drastic conditioning, we can preserve the probabilistic structure of the cone. We just take the base phi of u as our new normalized state space, and then we just take phi star of u as the new order unit. And the theory is equivalent to the system is equivalent to the system we have before. We've just renormalized things, which we kind of do in quantum theory once we have the result of an experiment. Maybe we want to, filter and then use the resulting state. Maybe it's an entangled state in some further experiment. And I'll just leave you with maybe one fly in the ointment, which is, well, if we like things that are in the interior of some cone, well, the automorphisms are on extremal rays of the cone of positive maps. So aren't they also idealizations too? How do you deal with that on this kind of intuitive picture of things? So I don't want to claim that all of this is worked out formally, but I think it's a nice way of thinking about homogeneity. And I think that's a good place to stop. So thank you for listening, and I'm looking forward to any questions you have.
Yeah, thank you very much, Howard, for a great talk. Does anybody have any questions? Okay, Lucian, I'll just unmute you here. Okay, go ahead, Lucian.
Hi, thanks, Howard. It was a great talk, and it was good to try to get to grips with some of this stuff. For me, so just a few questions. So in your strong symmetry spectrality proof, you get to the Jordan algebras just by imposing those two properties. And that I understand that's a major advance on work you've done earlier, where you had more structure. That's right, is it?
Yes. So the more structure was just one additional assumption, which was that there's no so-called higher order interference.
Yeah.
And higher order interference would be like you might have like a 3-path interference experiment where the interference pattern can't be constructed out of 2 interference on each pair of paths.
So that kind of relates to the simplicity axiom I'd used earlier, because I think it's very much related.
I think it's strongly related. So in your simplicity axiom had to do with the dimensionality of a composite state space. Is that right?
Yeah, you get these things high, which correspond to the higher. You get these higher possibilities higher in the hierarchy, which correspond to Sorkin's hierarchy.
You had that the dimension of the state space. I mean, on certain assumptions, the dimension had to go as the dimension of the state space, so the number of degrees of freedom to describe a state, needed to go as the as a power, an integer power of the number of perfectly distinguishable states. Is that right?
That's right. That's right.
Maximal number?
Yeah.
And then if that power is higher than 2, that was, I think at this point, you can interpret it as the existence of higher order interference in some sense, or at least higher order coherence. Because this higher order interference is really about the appearance of extra dimensions in the state space that you need to describe these three paths that you don't need to describe the coherences between any pairs of the paths. And so the number of pairs goes as the square, but if you have extra information to describe 3 paths, that's getting you above this, above needing the square of the number of distinguishable states.
Okay. And so you found a way to get rid of that in your case, this extra.
And it wasn't really by thinking about higher order interference in the end, it was just by directly proving. I mean, I spent a lot of time, looking for theories that have higher order interference and, in representations of groups, and you can find them that, seem to have it for certain measurements, but the structure gets very gnarly for general measurements, and there's no real sign that you could get arbitrary measurements having the higher order interference. So, it was a fun search, but eventually I decided, well, maybe I should, try the other one, which is stop trying to find a counterexample and just try to prove it. And that worked.
Okay, so that's interesting. So then if you, so now with those 2 axioms, you get down to the Jordan algebras, and then if I understand your remarks from earlier, does that mean you can just add something else, like, for example, tomographic locality, that gets you down to quantum theory?
Yes.
Or is that right? So really you have a set of three axioms which give you quantum theory in that case. And
so two axioms to Jordan and 3 to quantum theory.
Okay. Okay, that's very interesting. And then the other question I had was relating to the continuous reversible transformations axiom. So there isn't really very much in between the sort of permutation group and then the full set of continuous reversible transformations. So you could have something that sort of keeps an axis fixed and rotates around the equator, but that won't do much in that direction. And then you could have some groups related to the platonic solids. There isn't very much else. I understand. I mean, you probably would know more about this than I. So is it possible to have to slightly weaken the word continuous there to something like that? You demand that at least there are, at least there exist pure states within a product, which is bigger than some amount, and still get the same thing, or like, can you see a route in your approach to weakening the continuity requirement in that way?
Well, I do want to mention one conjecture which we're working on, which isn't exactly what you're talking about, or maybe it is. Maybe it would be an example, which is that I conjecture that you don't need to require continuously reversible pure state transitivity, that the theorem would actually hold with just transitivity of the automorphism group, period. That would be sufficient, and then you would get a slightly larger class, because of course you could get the classical systems in there.
Okay.
Right. I mean, the reason you don't get the non-simple Jordan algebras in general is that you might have 2 non-isomorphic summands, and you'll never get an automorphism that takes something in one summand to a pure state of one to a pure state of the other. So that's how we get restricted to the simple case. But yeah, so I think we could get some slightly larger case set of Jordan algebraic systems, including some of the, for example, simple ones where all the summands are isomorphic. I think we'd get that if we weaken the premise to transitivity of the full automorphism group of the normalized state space on the pure states. Maybe that addresses your second question a little bit.
Yeah, I think that
okay. So we're actively working on that.
Okay.
I'm hoping to get John van de Wettering involved in it. And yeah, we just need to set up a Skype. I've been busy with other stuff. It seems like the guy, just from reading some of his papers, I think there are ideas that can be used for that.
Yeah, because that's like that sort of thing happens in my more recent axiomatization, the one from 2011, where you end up getting. So I don't assume continuous transitivity, and you end up getting the classical case and the quantum case. So it's sort of similar to the possible thing you're outlining.
Oh, okay.
It's a very different set of axioms, I think. But,
okay. What is the paper, or which is the year?
I think it's 2011 or 12. It's a long paper called Reconstructing and Reformulating and Reconstructing Quantum Theory.
Yes. Let me have a look. Possibly,
but it's a different set. It's a different set of axioms. Okay. And one final question, since there's no other hands up yet, is what about time symmetry? That's something I've been interested in recently. So I guess in your context, that would relate to sort of some sort of comparison of the effect and state spaces.
Yeah.
Do you see time symmetry sort of as a consideration entering into what you do?
Yes. I mean, it doesn't necessarily especially enter into these two characterizations, but I think you can use it to characterize Euclidean Jordan algebraic state spaces, because I think it's related to self-duality. So I haven't fully worked out exactly why I think it's related to self-duality, but I mean, I sort of, maybe it was a bad idea, but no, I think it's I mean, it's saying that the state space and the effect space are isomorphic, and weak self-duality already says that. So you might also think weak self-duality is related to time symmetry, because if you think sort of heuristically, you can think of states, or particularly in a category theoretic formulation of probabilistic theories, which we often like to do, you can think of states as going from the tensor unit in your symmetric monoidal category, so that's just the real numbers, to your state space, or whatever the object is that corresponds to your system. And then the effects take you back to the tensor unit, back to the real numbers. And if you think of the sequence of these two things as kind of like a time ordering, then in some sense the effects are going, maybe going back to the order unit is like going backward in time. So anyway, I think it would go through self-duality and the Kosher-Windberg theorem, right? If you like homogeneity and you really think that self-duality encompasses some intuitively appealing notion of time reversibility, then you've already got a characterization of Jordan algebraic systems from Kosher-Windberg. I should point out that Alex Wills has a derivation or characterization in a paper, I think it's called Royal Road to Quantum Theory, where he uses self-duality and basically gets it from the existence of a composite of two systems with a perfectly correlating state. So it's a state that perfectly correlates the outcomes of one measurement, a measurement on the A system, with the outcomes of a measurement on the B system. And that in conjunction with homogeneity gets you, I believe, gets you self-duality. So I don't know exactly how the perfectly correlating observable is related to time reversal, but it's another thing that is close to self-duality. So I think understanding self-duality better is a good project, and there may well be people who've already understand it better than I do in terms of its operational significance.
So one thing that I haven't thought about time symmetry in the in this respect, but one thing that's been pertinent in my own ways of thinking about it is that the state space you normalize, so you end up cutting it off with a slice, whereas the effect space typically looks more like a sort of diamond in some sense. And so and that seems to go against symmetry, and one needs to find a way to deal with that. Yeah, so that's a problem for time symmetry in some sense.
Yeah, but I mean, yeah, but I mean, perhaps that has something to do with the way that we think about things, in that an experiment is imposing some time ordering, and that relates to picking out some special structures.
Yeah, I would agree with that. I think,
but yeah, it's an interesting question.
That's what it is. Okay, thanks.
Oh, thank you. Lev has his hand up.
Yes, so let's unmute Lev. Okay, go ahead.
Hey, Lev. Oh,
I cannot. Oh, maybe now it's okay.
Yes.
If there are other questions, maybe they have priority, because I'm not really have particular interest in Jordan algebras. And I'm here because I want to understand why so many people think about quantum mechanics and algebra and have no hint whatsoever what is the connection. Because I want to find connection between, study physics, in particular quantum mechanics, to explain my experience. And I have troubles to get it from quantum state. I kind of see it in a Schrödinger wave function in three-dimensional space. If I understand correctly, algebras talk about observables. But the first thing I started from quantum mechanics that observables don't have values. So if what I had, or maybe it's wrong, that people think that expectation values have something to do with connection to experience. But this I cannot understand. If I have a particle in two places, here and here, the expectation value of position is somewhere in the middle when there is nothing. So it has nothing to do with experience. So can you, or somebody in this forum, tell me how you connect algebra to my experience? Because in the end of the day, this is what science is supposed to explain.
Yeah, so I guess one thing I want, I guess one connection is that, at least the way I'm looking at Jordan algebras, is to concentrate on the probabilistic structure, the set of effects, and the normalized state space. And the effects can be interpreted as probabilities for measurement outcomes. And those are actually definite outcomes. So I haven't really been using too much about expectation values, except just to say that often the space that hosts the effects also is thought of as the space of observables. And that, that is usually because, in addition to having these outcomes that have different probabilities, there may be something of physical significance, some real number, say, assigned to the outcome, which doesn't directly have anything to do with its probability. But the real numbers assigned to that may have something to do with other aspects of physics that aren't encompassed just in this state space, that have to do with, certain outcomes are associated with position in space-time or with spin relative to some particular frame. And that's why I kind of emphasized that this is a very abstract way of thinking about state spaces, and you have to supplement it with more to get to sort of the meaty physics, where some of these observables are preferred because they, or let's say some one parameter groups of symmetries are preferred because they're the free evolutions of the system, and other other generators are preferred because maybe they can be coupled to other systems easily through interactions we understand. So I don't necessarily see this description of systems as encompassing all that physics. You have to use it in combination with other concepts like composite systems, or maybe the tensor product figures in some more complicated structure like topological quantum field theory, where certain algebras, if they're space-like separated, maybe you can represent them by a tensor product. So I guess I have a lot of sympathy with what you're saying, and I think that the general probabilistic framework addresses it to some extent by focusing at least on definite outcomes. And the focus on expectation values, I mean, maybe that originally arose in quantum theory in that when you do experiments with a lot of, let's say a lot of particles hitting a screen, going through your apparatus, initially maybe you see a distribution and you're concerned with the expectation value of the distribution, and you're thinking about random variables. But everything when you describe random variables in terms of expectation values, you can cash it all out in terms of probability distributions. So I don't know if that really addresses your point.
No. So if expectation value is not the issue and it's not kind of connection to experience, then you say you are concerned with probabilities of outcomes.
Yes.
But there is no problem about probability of outcomes. Shut up and calculate. It's excellent work. You don't have to do anything else. Physicists know how to shut up and calculate. Why do we need to introduce something else? Or it's just a technical tool which will help me to calculate? What is it? Because I thought that this is kind of a new way to understand the foundations. What is quantum mechanics? Mm-hmm. Because people who are not in foundations, they know to calculate everything. They don't need all this stuff, as I understand. Or maybe I'm mistaken, and this is for them, and it's not for me, because I want to understand the connection to my experience of all these abstract things.
Yeah. And so to some extent, maybe
to calculate probabilities, I know it's great. I have to teach some of these courses, and I have no problems. But I want to understand what is really there and how it's connected to my experience.
Yeah. So I guess another thing I would say is that, a lot of this general probabilities framework, and I don't want to oversell it because it's an interesting intellectual activity, but I don't necessarily think it's, the thing that's going to solve the problems with interpreting quantum theory, or maybe even the thing that will help us connect quantum theory with gravity and space-time in a more satisfactory way. It might help. It might help with that. But let's think of it this way. It's in part a way of understanding how what we can do with quantum theory compares to what one might have been able to do just as an abstract possibility in terms of information processing, let's say. And I think it's led to some insights in terms of understanding that certain things that one had claimed are peculiarly quantum and very special about quantum theory are actually general to all non-classical theories in this framework. For example, the existence of entanglement. And to rigorously prove that is difficult. And there's a recent paper by Guillaume Aubrin, and Martin Plavala, Ludovico Lamy. I can't recall if they have a co-author on that, so apologies. But well, I just want to say a little more. So, for example, the existence of entanglement is generically non-classical. The ability to do so information disturbance trade-offs are generically non-classical. The ability to do key distribution and distillation is generically non-classical. But for example, teleportation, quantum teleportation, steering are common to a much more restricted set of potential theories. They're much stronger constraints. So maybe we understand a little more about what's special about quantum theory compared to just any wacky general probabilistic theory we could have made up. And maybe that will be helpful in, understanding how to connect quantum theory with the real world in settings like relativistic gravitational physics, where it's maybe a bit problematic. Maybe it will help us with understanding the foundations, because we understand more what's particular to quantum theory and what isn't, or maybe not. But the last thing I want to say is intellectually, I think it's worthwhile to understand more deeply the nature of the information processing we can do in the theory we have, and how specific it is to that theory. And to some extent, I've enjoyed doing this for the last 10 years or so in general probabilistic theories, but I am kind of ready to branch out and connect more with the meaty physics of Hamiltonians and gravity and stuff. So, I think to some extent, maybe it is just an intellectual pursuit that's not for you because it's a bit too abstract and doesn't help us do specific calculations. And you might be able to look into literature and find specific calculations where some of the stuff coming out of the convex sets framework has been useful, but I'm not sure that that's necessarily the main point of this framework.
So maybe just again, this probability, general probability theory, any other theory, I think is as far from classical physics as quantum mechanics, at least. And quantum mechanics give us fruits. We see it can explain everything which I see around. So why would I look for another exotic theory, which until today didn't give me anything?
Well, okay, the other thing about the Jordan algebraic theories is that I think you may see some connections to physical systems. And because they embed in complex quantum theory, you can say, well, that is just sort of complex theory with some special super selection rules. So that may be a framework in which, looking at these spin factors as special subspaces of sets of spins, may relate to Majorana fermions or spin coherent states, and maybe it will give you better ways of calculating these. That's not really something I'm specialized in, but it's something I'm curious about. Yeah, but again, I'm not saying that this is the way forward to necessarily doing more with quantum theory, but I think it's helped people in quantum information understand to some extent, how their, why their protocols work, on the conceptual underpinnings of what we can do with quantum theory. And I agree, yes, as far as looking for new physics, it may not be necessary to look into these. One lesson that you get is that when you start putting in nice properties, you start getting back very close to quantum theory because you get these Euclidean Jordan algebras. So it's not easy to get to so one last thing I might say, though, while it's not easy to get to a theory where the full dual cone is the effect cone that has nice properties, you may also find that in many cases, a theory where you have a restricted dual cone that has nice properties, that might describe quantum systems with restricted sets of observables and states. And there's kind of a theory of generalized entanglement. We called it with Lorenzo Viola and Manny Knill and Gerardo Ortiz, that is related to just looking at what you can do with a subspace of the observables on a quantum system. You could formulate that as a general probabilistic theory, and it's related to group theoretic coherent states, so it's not completely, a new topic in physics. But there, I think some of these convex ideas may have applications to particular systems.
Can I just add a comment there? Like it does seem that, at least in this talk, you were saying that observables and states are both, describable in a Jordan algebraic framework, but also we know that 4 vectors and other kind of geometrical ideas can be, that we're used to using in physics all the time, can also be written in a Jordan algebraic framework. So I wonder if there's perhaps a benefit to being able to write all these familiar objects that we're used to seeing in physics in terms of a single language.
Well, it might be, and I haven't looked into this much, but if you look at the fact that in this Jordan algebraic language, you can formulate, Lorentz cones in higher number of space dimensions. And even the cones of these other Jordan algebras have nice properties like homogeneity that are shared, and pointedness, that are shared by the light cone in a relativistic theory. And then if you think about the fact that high energy people sometimes talk about our theory as being a lower dimensional, partial compactification of a higher dimensional theory, it might be that some of these Jordan algebraic structures would show up in the higher dimensional theory. And then you would find the more usual ones that we end up with in the lower dimensional compactification or approximation or slice or whatever it is. I haven't gone into that in any detail, really. But yeah, sometimes I'm surprised by the wacky ideas that high energy physicists entertain when, I tend to think of us quantum information and general probabilistic theories people as the ones entertaining wacky ideas. But then when you actually talk to high energy, hardcore high energy physicists who, compute Feynman diagrams and do lattice gauge theory, and, they're willing to entertain some pretty far out modifications sometimes.
True. Okay, Alex, do you have a question?
Yes, one second.
Unmute you here.
Yes, on page 8, you mentioned product of octonion matrices.
Yes.
Do you mean just standard row column product, or this is special bilinear map? Because product
Sorry.
we expect product of matrices to be associative. So the question, in this case, you mentioned just row column product of matrix, or you introduce some special bilinear map for this product?
So it's been a while since I looked at this in detail, but I mean, in general, the product of octonionic matrices is not going to be associative. And I think in the 3x3 case, you can come up with some special, probably bilinear map that it gives you a group. It gives you a group that's isomorphic to some, quotient of, it gives you a group that's isomorphic to whatever this exceptional group is. That's the automorphism group of the cone. But yeah, it's not just multiplying the matrices. And furthermore, you can't even do this kind of construction, for other dimensions of the octonions. I mean, other than 2x2, which is already one of the spin factors. It's the 9-dimensional ball. So Lorentz cone in, I believe, 10 dimensions. So yeah, you can't just do matrix multiplication to get the automorphism group of the octonions. But there is a different, I think you're correct, there is a different bilinear map. And I've forgotten the exact references. I mean, I do have the papers and I've looked at them. One of them is a physicist up in maybe University of Washington or Oregon, Tevian Dre. Yeah, Tevian Dre and his collaborators have looked at that a lot. But then there's some even earlier papers by mathematicians. So sorry, I can't give more detail, but I think you would find the references, at least in Dre's paper.
Okay, are there any more questions? Right, well, thank you so much, Howard, for your talk. And thank you, everybody, for your lively questions. Let me just see what's happening here next week. 1 second, or next time. I lost it. Okay. Anyway, at any rate, so at the end of January, so this is our last seminar for the end of this year, but our next seminar will be given by Sean Majid. I believe it's on the 31st of January. So Sean will be talking about, he has an associative construction of the octonions, which sounds surprising. So we'll be looking forward to hearing what that's all about. So thank you everybody for showing up, and thank you very much to Howard for such a great talk, and have a great Christmas.